Hello friends, today we are going to look at another numerical method topic, which is numerical integration. We first use trapezoidal rule to illustrate the method. So our objectives are to integrate a function numerically using trapezoidal rule. Trapezoidal rule falls under the closed form of the Newton-Cotes integration formula. Newton-Cotes formulas are the most common integration schemes used for numerical integration of a function. Here we replace a complicated function or tabulated data using an approximation function which is easy to integrate. So the general representation of Newton-Cotes formula is given below. I equals integral a to b f of x dx, where f of x is the function we want to integrate. We approximate it using a polynomial of the form fn of x. So I equals integral a to b fn of x dx. And fn of x is equal to a0 plus a1 times x plus a2 times x square plus up to an minus 1 times x power n minus 1 plus an times x power n. Here n represents the order of the polynomial. If n equals 1, as shown in figure 1, we get a first order polynomial which is a straight line. If n equals 2, for example, as shown in figure 2, we get a second order polynomial which is a parabola. Likewise, we can go n equals 3 to represent a third order polynomial, etc. So under trapezoidal rule, we are going to use n equals 1 as shown in figure 1. That is, we are going to use a first order polynomial which is a straight line. The trapezoidal rule for a single interval is obtained by fitting a first degree polynomial to two discrete points. Here I equals integral a to b f of x dx, which is equal to integral a to b f1 of x dx. Fn of x is the first degree polynomial in this case. And f1 of x equals f of a plus f of b minus f of a divided by b minus a times x minus a, where x is any point between a and b. So this relationship is obtained using laws of similar triangles from figure 1. So I equals integral a to b f1 of x dx. Here we substitute f1 of x into the integral. So we get integral a to b f of a plus f of b minus f of a divided by b minus a times x minus a dx. When you simplify this integral, we get I equals b minus a times f of a plus f of b divided by 2, which is the final form which we need to use the trapezoidal rule. The individual error is given as a negative of b minus a whole power cube divided by 12n square times fm double dash, but where fm double dash represents the mean of the second derivative of all the points as shown here, which is equal to sigma I equals 1 to n f double dash of xi of I divided by n, where xi of I is a point in segment I. The global error in this scheme is of the order of h square, where h is the interval size. So, and n represents the number of segments on equation 1. When you look at equation 1, if n is doubled, the error term becomes 1/4 of the original error value. So to reduce the error term, we should increase the number of segments again. Now let us do an example. We would like to integrate the function f of x, which is equal to 0.2 plus 25 times x minus 200 times x squared plus 675 times x cubed minus 900 times x power 4 plus 400 times x power 5 from a equals 0 to b equals 0.8. When we do this analytically, we can obtain a value which is equal to 1.640533. So we want to numerically integrate this function and compare our results to the analytical value. We can even change the number of segments n. So this is the MATLAB code for the trapezoidal rule. The function f of x is given over here, and our general rule is given here as I equals half times h times f0 plus 2f1 and so on. Our limits are a equals 0 and b equals 0.8. We initially assume the number of segments n to be 5, and the x values are given here, and the function f of x at these x values can be evaluated like here. So I represents the integration value. When we run this, we get 1.4848. So our true value is about 1.64. So there is some amount of error when you use number of segments n equals 5, which is kind of a low. We can now increase the number of segments from 5 to 50 and rerun this case. So here all these x values are given here, and the function f of x at these values are given here, and the final integration value comes to 1.639467, which is close, but still there is a little bit of error involved in it. So we increase the number of segments one more time to say 2000 and rerun this case, and we get a value of 1.640533, which almost matches the exact analytical value. To summarize, in this video we presented trapezoidal rule to numerically integrate a function f of x. F of x can be any continuous function, it can be a complicated function, including trigonometric, logarithmic, exponential values, etc., exponential functions, etc. We notice that trapezoidal rule is not a very efficient method. We have to increase the number of segments quite a bit to get more accurate value. The error is of the order of h square. In the next video, we can look at more efficient methods such as Simpson's 1/3 and 3/8 rules. Thanks for watching the video. If you have any questions, please post it. I will be uploading the course into your website. So the location I will specify in the video, in the YouTube location. Thanks for watching.